Okay, excellent. Well, our second speaker has also come to us from Singapore, working alongside Kellen. Xue Gong was at Edinburgh, now over in Singapore, and is going to tell us about some of her recent work. Over to you.
Thanks, Ben, for the nice introduction, and thanks to all the organizers for making this wonderful workshop happen. So there has been a lot of wonderful talks involving, especially those involving spectral graph theory and solving Laplacian eigenvalues associated with Laplacian matrices. So this is also somewhat related, but I'm going to look at it from a slightly different perspective. Specifically, we're trying to find the connection between solving eigen problems of Laplacian and random graph models. So I'll start with the basic graph and then directed graph and hypergraphs, higher order graphs. Right, so the data I'm going to consider here is the relational type of data. We only observe connections and relationship, but we don't have any other attributes such as location of the nodes. So the very natural first step is to embed the nodes into a lower dimensional Euclidean space. This has been widely used for visualization and can be also used in other following up tasks such as clustering, classification, or link prediction. Okay, so a standard approach is the spectral clustering, as everyone should have heard about. And this is related to this minimization problem where we're trying to assign each node to a real value, such that we minimize this total squared difference for all connected nodes. And this can be written as twice of the quadratic form of the Laplacian matrix. And this has been mentioned by Sergio as in the signal processing on graph. If you think of X as a signal, and this will be the total squared total variation. But we can also consider it as a position. So this becomes a squared Euclidean distance between the nodes. So in the end, if we embed the nodes with the, so we get a series of eigenvalues, assuming it's connected. So the first, the smallest one is 0, and we usually use the second one called the fiddle vector. And this will allow us to visualize the graph such that the edges are usually within between nearby or short range nodes that are close to each other. So its interactions are short range. Okay, so this has been some study on the random graph model associated with that. So Peter Grindrod proposed a range-dependent random graph model. So here P is a permutation vector. So we can assume we're assigning a ranking or order to each node. So the likelihood of the connection can be expressed as a function of the absolute difference between the ranking. Okay. And this should decay with the distance between the ranking, the likelihood. So later on, Heim showed that maximizing the likelihood of this type of graph, if the likelihood is given by this function, basically it's inversely proportional to 1 plus the e to the power of squared distance. So if that's the case, then we can solve a relaxed version with a fiddle vector. The relaxation happened here. So when we solve it, usually it's not a discrete set of permutation vectors. So we get the real value instead. So there's a relaxation from discrete to continuous value. Okay, so this type of range-dependent random graph might be familiar to everyone. It's very similar to the behavior we see in small world networks, and also is related to homomorphy. However, we may remember that in the small world, things are periodic. There's no clear starting and ending nodes, so we can plot all the nodes on the circle. So later on, they also proposed a periodic version of the range-dependent model. So instead of the absolute value, we take the mean of the difference and the n minus the difference, where n is the number of nodes in this graph. And with we can compute the log likelihood between the ratios of the periodic linear versus periodic model and if it's positive, then we can say it is more linear. So there's no real true value or true model or best model, but we can still compare or quantify the relative strength of models that are present in the data. Okay, so that's an undirected graph, and now I'll move to the directed case. It can be more complicated because there are more potential structure that we're interested in, and for example, that can be called periphery structure, where there's a central group that exerts influence to the periphery groups. That could be like a hierarchy structure, or that could be periodic structure. So this is the same data visualized by two types of algorithm. And so this is the East transcription regulatory network, where each nodes, there will be an edge from I to J, operand I to operand J, if I regulates J. So the blue ones are regulated, and the yellow ones are the regulating genes, and sorry, the red are regulating, and the yellow ones play both roles. So it'll be interesting to find which is the best way to visualize the roles of those different nodes. So that on the left, it's visualized using a directed false algorithm, where the edge direction push the nodes away. And on the right is visualized by Robert McKay with his hierarchical model. So in that way, we can assign a hierarchy, which is the height of the nodes. So yeah, so this is taken from the nice work by McKay in 2020. So it really depends on how we interpret the edge direction and how we want to visualize it. Okay, so there has been a few nice works on dark network, and this is not an exhaustive list. So there's a magnetic Laplacian by Fano et al. That assign the phase angle to each node, such that the edges tend to be point in the anti-clockwise way if we position the nodes on the unit circle. And there's an improved traffic level, which appeared in the previous images on the right. And by McKay, Johnson, and Sampson, there's a co-periphery detection by Tudisco and Heim, and there's a Hermitian matrix algorithm by Kikurin-Gu using a complex value matrix. And there's also random walk-based algorithm where we perform random walk along the edge direction by William and Zhang. So I'm going to mostly focus on the first two, just because they have a nice quadratic form or objective function associated with the scheme. So we're going to follow the similar line of thought, and where we're trying to find the connection between like a node embedding using this algorithm and the random graph models. So yeah, and another comment is also there's in the paper of Grindrod and Heim that we could also consider node embedding as an inverse problem, assuming there's an underlying random graph model that generates the structure. Okay, so the two models we're considering is the magnetic Laplacian by Fano et al. And the traffic Laplacian by McKay, Johnson, and Sansom. So the magnetic Laplacian is a periodic structure where you can map the clusters such that the edges are pointing to in an anti-clockwise direction, and there's no clear starting and end groups. And where in the traffic Laplacian, there's a linear structure. There's a base group, and there's a group on the top. So there's a clear starting and end group. So and this is so this is based on one of my work joined with Heim and Konstantinas Viglakis in Edinburgh. Okay, so I'm first just give you a definition of the magnetic Laplacian. So we're interested in mapping the nodes onto a unit circle or assigning them a phase angle lying between 0 and 2 pi, such that we minimize this objective function eta. So here the WS is a symmetrized version of the directed adjacency matrix. And then we calculate the square distance, kind of shifted square distance between two nodes, where there's an offset delta ij. Okay, so the delta ij is defined as -2 pi g times alpha ij. So g is a constant that gives you the distance between the clusters. And the alpha ij, it depends on the edge direction. And here is there are like 3 scenarios, whether that's an edge from I to j, from an edge from j to I, or it's both way. Okay, so minimizing this objective function is essentially finding k clusters on the unit circle such that the edges are pointing in the anti-clockwise way. Okay, so then the definition for trophic Laplacian. So here we're trying to minimize this linear incoherence. We can see that if we minimize, if we want it to become 0, then we just make sure that the level increased by 1 along every directed edge. Okay, so this is associated maybe ranking like football teams, or ranking the strength of players, who are the top, who are the. Okay, right. So we want to find a model, like random graph model, that's associated with Laplacian. And the tricky part for magnetic Laplacian is that we know the offset delta term depends on the edge direction. So we need to think about random graph model that could like consider different types of edge direction. So now we consider this type of model where there's 4 scenarios that are generated independently with different probability. So there's a scenario ij has a reciprocal edge, and the scenario I to j, scenario j points to I, and there's no connection. So they're described by function fql, and we make sure that all 4 scenarios has likelihood between 0 and 1. And then we did the math by matching the objective function with the log likelihood of the graph. So the log likelihood graph, we will need to consider all 4 scenarios and like sum up the log likelihood of all the edges that are absent, or either absent or present in the data. Okay, after matching the terms, we arrive at this expression for the model for f, q, and l. It's a little bit hard to see just from the formula. So beta ij is the difference between the phase angles. But if we plot them, and so this is more like a softmax function. So whichever is the max is more likely to happen. So basically, it's saying that if theta I minus theta j equals to 2 pi j, we're more likely to see theta I sitting, this is an edge from j to I pointing the anti-clockwise way. So that's a way of interpreting that. Okay, so this we call the directed PRDRG model, just because we incorporate the edge direction to the PRDRG model. Okay, so the trophic Laplacian is slightly easier because there's no edge direction in the quadratic objective function. So we can assume a simpler type of model where we have either an edge from I to j or no edge from I to j, and the edge from I to j and j to I are generated independently from each other. Okay, whereas in the previous case, these two are not independent. Okay, so even similar procedure of matching the quadratic form with the log likelihood of the graph. And also we need to assume a discrete constraint, just because there's a term associated with null graph that we want it to be constant. So after this discrete constraint, we arrive at this model where it looks very similar with the what Haim showed earlier. So the likelihood is, if you take the log likelihood, it's inversely proportional to the 1 plus e to the power of gamma. Gamma is a free parameter, and this basically measures the incoherence of the edges. Okay. So in the real data, we don't know the gamma, and therefore there's various ways to approximate either by maximum likelihood, or we can matching the like edge density. Okay, so this is a more general form where we can assume different incoherence function and have the associated random graph model. And this allows us to compare two different models and say which is better model or better algorithm to embedded nodes in this data set. Of course, we're not saying this can find the best model because there's infinite many number of models you can find. And also, you might want to make sure that the number of parameters are similar in the models you compare to make fair comparison. Okay. So this is a synthetic graph we generated using the PRDRG, and indeed we have a wrap-up effect here, where the last group tend to be connected to the first group, and we try to reorder it with magnetic Laplacian algorithm and trophic Laplacian algorithm, and found that the trophic Laplacian is not able to find the periodic pattern or find the correct cluster here, just because it couldn't tell which is the first group and which is the last group, because there's no first and last group in the periodic structure. And furthermore, we substitute the embedding learned into the model, and now we can compare the likelihood of the two models. And in this case, the magnetic Laplacian model gives you a higher log likelihood for all the parameter gamma we tested, because this is unknown. This is, okay, so here is a point estimate of the gamma. And okay, and more interestingly, we did some experiment on the real network, and this is the ecosystem or food web from the Florida Bay, where there's the edges represent carbon transfer of predator and prey relationship between the fish. Okay, so on the left, we have the trophic level, where we can find some species on the bottom of the hierarchy, some higher in the hierarchy. And using the magnetic Laplacian, we can find some interesting directed clusters, some directed triangles. And the blue edges represent the edge that kind of align with our assumption of the structure, while the red edges are points in the reverse direction. And in this case, the magnetic Laplacian is able to produce more coherent edges with the structure we assume. And we plot the likelihood this agree with the previous observation as well. Okay, so furthermore, we did more experiment using a set of various data from social network and biological network, and compare the log likelihood between the periodic version and the linear trophic version. And the positive value on the top basically suggests that the structure is more periodic. So we have Florida Bay food web, influence matrix, basically how different factors like social economic factor influence each other, like the data is acquired by survey. And US migration network between states, US economy IO input output between different sectors, which kind of map the supplier and demand kind of relationship between different sectors. And international trade, I think US transportation, flight network. So those are more periodic, which kind of makes sense. For example, the flight, they need to come back in somehow to the region. And on the bottom, we have the graph that are more linear than periodic. For example, the C. elegans neural network, because it's a linear tube-like structure. And East gene transcription network, political block, shopping basket, venereal open, and word adjacency. Okay, so now we've looked at the directed graphs, and so the next extension is to hypergraphs, which contains more than the edge contain more than 2 nodes. And yeah, so there's a various approaches of analyzing it, either using matrix or tensor. So we've heard a lot about from previous talks, and there's also various generative model being proposed, like Chojo, Veld, and Benson. They proposed a kind of stochastic block model, like generative hypergraph model, and I think Rubens is going to have his model coming out soon, so I'm really looking forward to it. And so can we also say something about the connection between the spectral embedding and the hypergraph generative model? So this is based on John work with Desheim and Konstantinas Zigalakis in Edinburgh. Okay, so I have to say we chose the matrix version just because in real data, like hyperedges may come in different sizes. So it's a kind of more straightforward choice, considering we're using some social hypergraph data. However, we also want to consider like different hyperedges with different sizes. So we somehow adopted the flattened adjacency matrix, where the WT captures only the hyperedges of cardinality T that contain T nodes. Okay. Right. So the Wij will count the number of edges between node N and node J with cardinality T, and we can compute the diagonal degree matrix similar to the standard graph. And the Laplacian matrix is also of order T is also defined in the same way. And by doing a linear combination of all orders of hypergraph up to cardinality T, we get the hypergraph Laplacian matrix. So this CT is a positive coefficient just to allow for tuning of the importance of different cardinality. For example, in the epidemic spreading, the larger hyperedge might speed up the spread, so we may want a higher weight. And like in friendship network, the pairwise friendship might be stronger than the friendship between the group or any social contact network. So you might want a bigger weight on the smaller T. Okay. Right. So we could also have a linear and a periodic version in a similar flavor. And in the linear version, we could embed the nodes using the fiddler vector of this hypergraph Laplacian. And in the periodic embedding, we want to find the phase angle, but we need to use some heuristic to find the angle because we'll get real valued eigenvector. So we will take the theta to be the arctangent of the fiddler vector divided by the third smallest the eigenvector. Okay. And the model is described as follows. So X is the embedding of the nodes. So we have n nodes, and R represents unordered set of nodes. And this unordered set R can either be connected or disconnected. And the connection probability is given by Fxr, and it is inversely proportional to 1 plus the exponential of gamma Cr and times I. Gamma is a free decay parameter controlling how quickly the likelihood decay when the nodes are further apart. Cr is the weight of the cardinality R you assign to the graph, or you somehow fit to the data. And I is the incoherence that measures the total squared Euclidean distance within between all pairs within the set R. Okay, and obviously it can be different from between the linear and the periodic version. So in the linear version, we have the norm square of xi minus xj, and in the periodic version, we'll have the e to the I theta I minus e to the I theta j norm square. So that's a difference between the linear and periodic. Okay, so so I'm going to show some numerical results with this. Okay, so this is the data of high school contact data acquired by Mostranda, Fornat, Barat, and also analyzed and uploaded by Chojo, Veld, and Benson. And this is collected from a group of high school students in France, with students wearing wearable gadgets in front of them that register a signal if two people are getting close to each other, like within 1 to 1.5 meters for around 20 seconds interaction, and they will register a signal. And in that way, we can capture not only that, like pairwise interaction, but also higher order interactions, and generates this hypergraph data. And here we truncate the data and keep only the second order and third order interactions. So we remove anything, all the edges with cardinality larger than 4. And then perform the spectral embedding with a linear model, linear algorithm, and the periodic algorithms. Okay, so once we get the embedding, that can be substituted into the random graph model we derived earlier, and that can be in turn used to calculate the log likelihood of the graph, how likely we're observing the graph given this model. And in the real data, we don't know exactly what's the weight of different cardinalities. So we scan a range of C3 and plot the likelihood. So here we see the periodic version achieves a higher likelihood over our range of C3 scanned, suggesting that like in the high school interaction, like there's no marginalized group, such that the periodic clustering is a more proper way of clustering or visualize the interactions between the students. Yeah, and also the data come with the label of their classes, so we can also do spectral clustering. And this is basically embedding followed up by a k-mean clustering. And we plot the ARI, adjusted rand index. So it's computing how the true cluster compared, how the learned cluster compared to the true cluster after adjusted for the different sizes. Okay, and here most of the time we see the periodic version also perform better in clustering. Okay, so another comment is that here we're not exactly trying to answer should we use higher order or not, but we can still see that if we use the positive C3, so basically we consider hypergraphs with size 3, we can get better clustering results. So in that way, the higher order interaction is useful in this data set. Okay. Right, so this is another experiment we did for edge prediction. Like, so in the first 3 lines, we're trying to use the syntactic data generated from the linear hypergraph model. And on the 3 bottom lines, we're using high school data. And in the bracket, we split the data by train and test. So in the syntactic model, there's no time step, so the data are just randomly splitted by the ratio. And so by data, I mean the hyperedges. And in high school data, there's a timestamp. So the data is splitted by the time. So here we mean we learn from the first 80% of the time and then train on the last 20% of time. Okay, and there's a few algorithms previously mentioned by Benson et al. And we also list random baselines with assign a random probability to the hyperedges. And okay, so this is the prediction from the linear model, and those are some baseline models. So arithmetic mean, geometric mean, and harmonic mean. So basically, those methods are counting how many times the nodes have been connected in hyperedges in the training data or in the past, and take the average between all paths within the triplets. So if it's the average high, then it's predicting new hyperedges. If the mean is low, then no hyperedges. So it's basically counting the past, use the past to predict the future. Okay, so our model is our prediction is a model based. We use the model compute the likelihood based on the distance between the embeddings and then assign the likelihood to each possible hyperedges. So in the synthetic data, so all the numbers here are computed using the area under precision and recall curve AUC PR. And in the synthetic data, our model performs better than the simple like means using historical data and for all split. In the high school data, we observe that when the splitting ratio, when the training data is enough or is sufficient, a simple geometric or harmonic mean will perform best. This is understandable since if we have enough history, then we can just assume that history will repeat itself. So it's a relatively easy learning task. However, if the training data is insufficient, if we only use the 20% data for training, and our linear model will achieve a higher precision area under precision recall curve. So in that sense, like when the data is sparse, the model might be useful for learning the future interaction. Okay, so this part I'm going to mention briefly. So this is not related to any generative model, but I think it's also interesting, and we can definitely discuss more afterwards. Right. So, okay. So I've talked about magnetic Laplacian, and it's actually related, a special case of a connection Laplacian. So in the connection Laplacian, we can assign a rotation between nodes. This rotation can be one-dimensional, higher dimensional. It's basically an orthogonal transformation between two nodes. So if we go to simplicial complexes, so we're curious that can we find magnetic Laplacian or its higher order version connection Laplacian that can capture the rotation between not only nodes but maybe edges. Okay. Right. So so in this work, yeah, I think I might miss a slide, but yeah, in this work with Genestra, we're trying to define the higher order connection Laplacian for simplicial complexes, such that we can capture the rotation between nodes over the common the edges, or their shared edges, or rotation between edges via their shared triangles. And we did some theoretical analysis on the magnetic Laplacian and run some numerical tests. For example, we can discretize little a torus, a directed torus, and compute the one-up Laplacian matrix, and so here is basically what is more complicated when it comes to higher order, because we not only have the direction on the edges, but we also have the direction in the triangle. In that way, we have more possible scenarios, and we want to differentiate a different scenario by assigning a phase angle, a rotation angle between the edges. So here we use a polymatrices. So in that way, we will assign each edge with two phase angles once we compute the eigenvectors of the Laplacian matrix. So this graph plot one of the phase angle theta of the one-up Laplacian. And we could see that if we walk along the direction of the edges, we will recover a periodic pattern of green, orange, blue, and green, orange, blue, and so on. So this is quite interesting to see that we can incorporate the directional pattern on the simplicial complexes. Okay. Right. So now I'll just summarize the previous works I've talked about and so basically spectral embedding, we can rethink of it or restate it as a inverse problem, assuming that the data come from a certain type of generative model. So in the two works I presented earlier, we analyzed the periodic and linear embedding algorithm for directed graphs and hypergraphs and associated the related models. And this model allows us to quantify the relative strength of different structures that are present in the data. So far, we compared two structures, but there's many other possible structures, such as periphery structures or echo chambers, many interesting patterns in the social network that we can visualize. So how can we compare different structures, especially when the number of parameters are different? And can we find random graph interpolation on the simplicial complexes? We've heard some interesting talk today, but I think there's still a lot of open questions for simplicial complexes. And also, so far the data are pure relational, and there's no position, no location of the data. So what if the data lies on a manifold? Can we incorporate those geometric information in the either objective function or the random graph model? Okay, so currently I'm also looking at the biological data that Curly mentioned earlier, because now we're working in the same group in Singapore. So those also open up many interesting questions in terms of the topology or the geometry of the data. So if any one of you are interested in either like topological data analysis on BAM molecular data, or directed simplicial complexes or random graph models, I will be very happy to chat about it. So I'll be here for the next week. So I think it's a really interesting area to work with. Okay. So with that, I think I'm going to stop my presentation. And if you have any questions, just feel free to ask.
That was great, thank you. Do we have any questions?
Okay, so the question is how to learn the parameters in the magnetic Laplacian. the parameter here we have is basically mostly it's basically g, the distance between the clusters. And so usually we're interested in integer number of clusters. So we basically consider like 1, 2, 3, up to 6 cluster, because that's usually what people are interested. So in that sense, we, yeah, I didn't show the graph here, but we did the grid search for different number of Ks. Okay. Yeah, it's similar with what we did with gammas for the decay parameter. So we scan K from 1 to 6 and find the K with the maximum likelihood, and then use that the best K to compute the likelihood of the model for this graph. Yeah, so it's just other ways of doing that. Yeah, but all the parameter estimation here we did are based on grid search, because we found it in the noisy data is really more robust than like matching a certain statistic of the graph, such as matching the density. Yeah, so yeah.
I had a question. Oh, actually, it was on that slide that you just showed, the one that had the Florida Bay. So I think you said that this one was better described by the periodic model. So my question was, does that relate to some biological property of that network? Or how does that mathematical result relate to our understanding of the sort of biology of that food web?
Oh, yeah, that's a really interesting question. And like, so here it seems that the periodic structure is more coherent than this way, than the linear version. And it's not suggesting that like 3 species like prey on each other, but it's basically there are 3 groups when you map it, that one group prey on the other, and the second group prey on the third group, and the third group prey on the first group. So it's quite interesting pattern, but it's not impossible in the biological network, and it's especially if we include other like inorganic kind of elements in the network. So it's happened kind of more often than I would thought in the data. So it's kind of suggesting that assign a trophic level to each species may not be the best way or most faithful representation of the data of the food web that we see in the real life. Yeah, but I'm not a like fish expert, so I would definitely be quite keen to hear anyone who's more familiar with the peculiar behavior of the fish.